So 7.4 will be about solving basic trig equations, emphasis on the word basic. I just want to start off small today, and then eventually we'll graduate up to the more interesting equations. Now, for the first half of Unit 7, we spent a lot of time talking about identities and ways to manipulate trig expressions, ways to rewrite them, make them look differently, how to manipulate these sines, cosines, and tangents. But we really didn't do anything. The second half of Unit 7 will be actually doing stuff, solving equations, finding answers, so on and so forth. Well, when you solve a trig equation, you are asked to solve for answers. You're always going to be asked to solve for x or theta or whatever it is. So it sort of makes sense that we need to be adept or be experts at angles. Let's go ahead and just take a look at a quick example here. So what is an example of a trig equation? Say I ask you to solve for sine theta equals 1/2, right? This is a very basic trig equation, no bells and whistles, so on and so forth. Well, to solve a trig equation, you're solving for the variable, theta here, and it's just regular algebra. Use inverse operations. To get this theta by itself, we have to get rid of the sine. I'm going to show my work here, even though typically when I do this on my own, I just go straight to the answer. So let's just pretend we don't know any better. Gee, I want to solve for theta, get rid of the sine. What's the opposite, or how do I get rid of a sine? I have to use this inverse. So we'll take the sine inverse of both sides. Right? So just regular algebra, inverse operations. What you do to one side, you do to the other. So you end up with this expression, theta equals sine inverse of 1/2. Now remember that inverse trig functions is always asking you a question. What angle? So this is asking you what angle has a sine value of 1/2. Now, although this is a basic question that I expect everyone to be able to answer, let's still go under the guise of we don't know any better. And I actually want to see this visually. So, well, I guess that's the only way to see things, right? Visually, that's redundant. I sort of want to look at the graph of what's going on here. So if we take a look at a unit circle, and I'm just going to put them on a coordinate system here. So here's a coordinate system. I think that looks circle-ish. Let's try to center him. That's not good, but close enough. Actually, it's not close enough. I'm going to do it this way. Sorry, guys. Things have to be perfect. Yeah, I can still see it, but whatever. What am I asking you? I'm asking you to find all angles where the sine value is 1/2. We have to remember that on a unit circle, the y value, I'm going to use theta, x is confusing. The y value corresponds to the sine of that particular angle. Now, if this is a unit circle, this is 1 and 1. So 1/2 on the y value, I'm thinking of y's because I'm looking for sine, should be somewhere right here. So basically, I'm asking you to find all angles that have this particular y value. And clearly, just from the picture alone, we can see that there are two answers. This angle here, wow, that was a bad line. And this angle here. So we should know that we have two answers. This angle, which we should know is 30 degrees. In this section, or in math in general, we like radians, so I'll use radians here. And then this other angle over here. Now, we should know that that angle has a reference angle pi 6 because they're symmetrical, which means this guy here, I'll call him theta sub 2. I'll do it down here. Theta sub 2 is 5 pi 6. So there we go. We can see that within one full circle, that is to say, within the interval 0 to 2 pi radians, the equation sine of theta equals 1/2 has two solutions. Theta equals pi 6 radians and 5 pi 6 radians. Okay. But here's the interesting thing. When you're solving a trig equation, you're solving for an angle. And yes, angles can be represented by the amounts of rotation in a circle, right? So if I were to take a ruler here, ignore the degrees because it only measures acute angles. Notice I go up to 90 and then goes downwards. It should be counting upwards. But if we're measuring angles within a circle, they're unbounded. What does that mean? That means if I were to keep cycling over, here's 180 degrees. Again, ignore the numbers because it doesn't measure properly or only measures acute angles. Here's 270 degrees. Now I'm approaching a full circle, so this is approaching 360 degrees. Because angles are unbounded, this is technically 361, 362, 363, 364, 370 degrees, 380 degrees, 390 degrees, 400 degrees. Degrees are unbounded. You can go as high as you want in terms of the number of degrees. But since they are physically stuck within a circle, lots and lots of degrees will overlap with each other. This is what we called coterminal angles back in Unit 5. Two different angles, numerically, that share the same position. So let me switch colors here. Let's see. Yeah, you guys can see this one. So notice how we've marked two answers here, the black angle and the blue angle. Well, technically speaking, this angle that I draw, doesn't it end on the same spot as the black angle? Yeah, so it should have the same y value. In other words, it is another valid answer to this equation if we go beyond a full circle. Well, how did I get to that answer? Notice we had to travel around a full circle. In other words, so that's sort of like the big idea. You can generate more answers by moving a full circle. Or let me, not by moving full circles. Let's make it plural, because I can move in a full circle once, a full circle twice, a full circle 3 times, so on and so forth. So, sine theta equals 1/2 has answers. Theta equals pi 6, as we said. But I can get another answer by doing pi 6 plus a full circle to pi, right? But I could also move another full circle. I can get another full circle by adding 2 pi's, right? That's adding 2 full circles. But I can get another answer by adding another full circle, so maybe 3 full circles. Or what if I add 4 full circles? So on and so forth. So I hope everyone can see that we can always generate another answer by moving in a full circle. Mathematically, in terms of the angles, how do we move in a full circle? You just have to add full pi's to them. But of course, we can always go backwards, right? You can get coterminal angles by subtracting a full circle, or subtracting 2 full circles, or subtracting 3 full circles, so on, and so forth. Okay. So when you answer these questions, am I going to expect you to write down all the possible answers? Of course I am. But of course, I'm also, not a sadist. I'm not going to make you spend your entire lifetime writing down these answers, because there are an infinite number of them, and you'll be spending the rest of your time doing it. So there needs to be a mathematical way to describe all of these answers. Notice how each answer has the same pattern. They start with the basic answer within a full circle. So notice how every single answer has a pi 6 in it. So you definitely start with your basic answer. Notice how every answer has a variation of 2 pi's in it. The only thing that differs are, I'm running out of colors, let's use blue, right? are the numbers of 2 pi's, right? We could have 1 positive 2 pi, we can have positive 2 2 pi's, we can have positive 3 2 pi's, or we can have negative 1 2 pi's, we can have negative 2 2 pi's, we can have negative 3 2 pi's. So the way that we would write this answer down is the original answer plus, because I'm adding a random number of 2 pi's, we're going to be adding multiples of 2 pi's. We could add 2 2 pi's, we can add 5 2 pi's, we can add negative 7 2 pi's, so on and so forth. The way we write that down is 2 pi times k, where k is just an integer. So this weird looking z symbol here is the mathematical way of saying an integer. This is the mathematical way of saying that your answer is pi 6, but this plus 2 pi k business says you can go around a full circle as many times as you want to generate another answer. And this just declares that this variable k here, or this parameter k here, it has to be a positive or a negative whole number. That right there will give me every single answer possible from this location. But of course, we also know that we have this location. So you're going to do the exact identical thing, right? So my answers would be 5 pi 6. That's the basic answer, but we can generate an infinite amount of more answers by going around in a full circle. So we have plus 2 pi k and declare that k is an integer. That right there is what we call the general solution, or the full solution to the trig equation sine of theta equals 1/2. So it will require a little bit of thinking. It will require you to solve trig equations within one full circle, but then afterwards you have to mathematically generalize your answer. You have to mathematically find all of the other angles. And remember, to get more solutions, you just have to find coterminal angles. Other than that, the only knowledge necessary to solve trig equations, or basic trig equations, is regular algebra and your knowledge of special angles. So if we do another example, suppose I ask you to solve, or let me rephrase it this way. Find the general solution and, so this is a two-parter, list 6 specific solutions to cosine of theta equals negative radical 2 over 2. So I picked this example because the instructions changed a bit. It asks you to list specific examples, and because I tossed in a negative there. So what happens when you have these monkey wrenches? Well, the first thing I do personally, so this is a Mr. Vo thing. This is not what every math teacher does. This is what I do. When it comes to trig and positivity or negativity, I typically ignore it because I know how to take care of quadrants at the end. So the first thing I'm going to do is I'm going to ask myself, I'm going to switch colors. So this is what I'm thinking. I'm going to think to myself, what angle has a cosine value of radical 2 over 2? Again, notice I ignore the negative because I'll take care of the negative at the end. And I hope it doesn't take a lot of thinking, because those are side lengths of special right triangles, that you guys know that the answer is 45 degrees, or pi 4 radians. But there's always a big but in math. We had cosine of theta equals negative radical 2 over 2. Negative. So I asked myself, I got to fix my handwriting, negative. So I asked myself, where is cosine theta negative? Again, all of these questions I'm asking myself should be easy questions for us to answer, since we know we've gone through Unit 5 and 6 and spent the first half of Unit 7. So the answer, of course, where's cosine negative, is in the second quadrant and then the fourth quadrant. So now knowing that my reference angle is pi fourths, I just have to put pi fourths in the respective quadrants. So there's pi fourths, here's pi fourths. So now we can actually answer the question. So let's answer the question. Solve cosine of theta equals negative radical 2 over 2. I know one answer is going to be right here. And then the other answer is going to be right there. So let's do the first answer. If you have a reference angle of pi fourths in the second quadrant, that should give us 3 pi fourths. And if you have a reference angle of pi fourths in the third quadrant, I'll call it theta 2, that should give us an answer of 5 pi fourths. But do you see here how visually, I'm going to write stuff down, but I'll erase it later. We can always generate more answers by going in full circles. Let's pretend I'm right here. I can get another answer by moving a full circle. If I started here, I can get a completely new answer by going in a full circle. So I have to account for that when I write down my general solution. So in general, the solution to this answer is my basic answer, 3 pi fourths, plus I can go around in a full circle. So mathematically, we write that as plus 2 pi k. I can also start at 5 pi fourths plus and go around in a full circle plus 2 pi k. In either cases, I'll be lazy, I'll do this. In either cases, k is an integer. You have to declare what k is or else the reader will not know. So this is the general solution. But the instruction also said to list 6 specific answers, right? Yes, list 6 specific answers. Well, once you have the general solution, to figure out the answers, it's just like following a formula. Just plug in k values. K could be anything you want, but they have to be an integer. They have to be positive, negative whole numbers. So I don't know. No, to get the 6 specific solutions, plug in any k values, plural, you want. So I'm going to use, I don't know, I'm lazy. Let's pick small numbers. K equals negative 2, negative 1, 0, 1, 2, what's 1, 2, 3, 4, 5, and 3. That's the 6 ones. Right. So the 6 specific answers would be 3 pi fourths plus 2 pi times negative 2. And then you just have to figure that out. So that's a negative 4 pi, which is a negative 16 pi fourths, which is a negative 13 pi fourths. That's one specific answer. 3 pi fourths plus 2 pi times 1, or negative 1, excuse me. So that's what, negative 2 pi, that's negative 8, so that's a negative 5 pi fourths. So finding the specific answers, I hope you guys see, it's just arithmetic. Just do math, add, subtract fractions. 3 pi fourths. 3 pi fourths plus 2 pi times 1. That's, what's that? 8, 11 pi fourths. And then 3 pi fourths plus 2 pi times 2. That's going to be 4, 16, 19. 3 pi fourths plus 2 pi times 3. That's going to be what? 6, 24, 27 pi fourths. So here are the 6 specific solutions. And I can keep going on and on and on to generate specific answers, but the question only asks for 6 of them. So again, general solutions is like sort of like a formula to generate all of the answers. Specific solutions is when you plug in specific numbers for k to get actual angles. That's about it. That's Ooh, erased too much. That's solving basic trig equations, just understanding that we're not solving for numbers per se, we're solving for angles, and angles are cyclical, so you might have an infinite amount of answers, and you have to be able to write all of the answers down in an appropriate manner. Let's do another example here. Suppose I ask you to solve tangent of theta equals 2. Okay. Now I picked this example for two reasons. Number one, we haven't done a tangent example yet. And number two, in terms of the special triangles, oh no, there is no special angle that has a tangent value of 2. I can't think of the 36 and 90, 45, 45, 90 and do a tangent that gives me a 2. So here's sort of the idea. If you're not given special ratios, use a calculator. That's it. That's the only thing I wanted to show in this example. So we get theta equals, to get rid of this tangent, we have to use inverse tangent. So according to my calculator, in radian mode, I'm going to get, if I type in inverse tangent of 2, I'm going to get about 1.12 radians. But you got to remember, so I'm going to switch colors, so this is what you're thinking. This is asking you what angle has a tangent value of positive 2. And we should know, being good math students, that tangent is positive in the first and in the fourth quadrant. So the answer that the calculator gave me, 1.12 radians, is a reference angle in the first quadrant. Oops, not degrees, radians. And in the second quadrant. So technically, we have two answers, as always. We have this first answer here, and we have the second answer here. So normally, that would require us to write down two general solutions, right? 1.12 radians plus 2 pi k, and then, pi plus 1.12 plus 2 pi k, so on and so forth, right? So technically, we should have two separate answers here. So this answer, I'll call it theta 1, is 1.12 radians. And then in a different color, see how this guy, it goes beyond 1 full pi. So theta 2, since it was a calculator answer, I'm not going to do decimals. I'm going to just write it like pi plus the reference angle. Right. So technically, this problem does have two separate answers. And then to do the general solutions, we would just do, okay, 1.12 plus 2 pi radians, 2 pi k radians, and then pi plus 1.12 plus 2 pi k. But notice how these answers here they sort of symmetric. They form a straight line. So if you do the 2 pi k business, visually, this is what's going on. You're saying, hey, start with this answer, and then to get another answer, go a full circle. Then go another full circle. Then go another full circle. Do you see here how we're completely bypassing this answer? Well, it's not very efficient, because then you'd have to say, okay, once that's done, start at this answer, and then to get another answer, go full circle, go full circle, go full circle. You're completely bypassing the other answer. It's completely inefficient. We should notice that there's some natural symmetry here, that if we start at this answer, you just have to go a semicircle, half of a circle, half of 2 pi, which is 1 pi, to get to this answer. And then once you're at this answer, to get to the next answer, you just go another pi, then another pi, then another pi, then another pi. So the moral of the story is, if you recognize that your answer is symmetric, that it evenly cuts a circle into equal pieces, do not give me separate general solutions. Merge them together, blend them together as one answers. So here is our answer. Our general answer. You can start at any answer you want. I'm going to go ahead and start here. So that's going to be 1.12. But instead of adding a full pi, if I start here. To get to my next solution, I just have to add half of a circle, so it's 1 pi. So instead of adding 2 pi, you're going to add 1 full pi to get to my next answer. That's going to be pi k. And of course, declare that k is an integer. So that's all I have in terms of technique, in terms of ideas to solve trig equations. Be mindful of where your answers are. Write down the general solutions. And if you notice that there's some metric, go ahead and condense your general solutions into one. Now, the only way I can make this harder, and I'm putting harder in quotes even though you can't see it, is if I make you do a little bit of algebra first. But it's just the same things you've learned in Algebra 1. Use inverse operations to get the variable by itself. So suppose I ask you to solve this question here. 2 sine theta minus 1 equals 0. Well, before I can use inverse trig functions, I have to get the sine theta by itself. So it's just regular algebra, right? This should be child's play for everyone. We would add 1 to both sides first, divide out the 2, and then you can use the inverse sign, right? Theta equals sine inverse of 1/2. I should not need a calculator because 1/2 is a special side length, special ratio. We should know that the reference angle, I'll put a line over it to indicate reference angle. What angle has a sine value of 1/2? That should be 30 degrees or pi 6 radians. What quadrant is sine positive in? Because this is positive. Sine is positive in the first quadrant and in the second quadrant. So if I put my reference angle of pi 6 in those quadrants, what are my actual answers? So my first answer is, of course, pi 6. And my second answer is 5 pi 6. Notice how these two answers do not cut the circle equally. That is to say, if I start at one answer and go to the other answer, and then from that answer go back to the other answer, they do not have equal angles. So I'm going to need two separate statements here. So if I start at this angle, to get to my next answer, I have to go a full circle. So it's plus 2 pi k. And same thing for the other answer. So there is the general solution to this equation. Okay. So notice how I drew a little picture when solving. This is just a habit I got into. It helps prevent me from making mistakes. It helps me put the reference angle in the right quadrants. And it also shows me if I have any symmetry or not. It's sort of nice to see that. So let's do one last example here, just like a non-straightforward example. Suppose I ask you to solve tangent squared theta minus 3 equals 0. So pretty straightforward algebraically. Add 3 to both sides. And I will show my step here, to get rid of that square. Everyone knows you should do the square root. But remember, we are solving an equation. The context is still solving an equation. Even though it's trig, we have to remember from algebra, anytime you take a square root to solve an equation, your result will be plus or minus. And then we can go ahead and take the inverse tangent. So remember, when it comes to positive or negatives, I really just ignore it and just do reference angle. So what reference angle has a tangent value of radical 3? Right? Radical 3 is a special side length. So if you think of your special triangles, the 30, 60, 90, 45, 45, 90, hopefully we can see that this guy has a reference angle of 60 degrees or pi 3 radians. Now I go ahead and visualize where the answers are. Notice how it's plus or minus. So it's basically everywhere because every single quadrant tangent is going to be positive or negative. So I have an answer here, 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 and the reference angles are all pi thirds. So notice that we do have symmetry along the x's here. So I do not need 4 separate statements. At the very least, I need 2 separate statements. But is it possible I only need 1? Now, I just drew a sketch, so it's not to scale, but is it possible if I go here that I can just simply bounce from one answer to the next answer to the next answer? In order to determine that, you just have to figure out the amount of angles in between. So I hope it's very clear to everyone that this right here is 2 pi thirds. This right here is 2 pi thirds. What about these guys over here? Well, we should know that in a full, we should know that this right here is 1 full pi, right? Half a circle is 1 full pi. So if we just have to do some geometry with this, with some algebra. If this is 1/3 pi's and this is a 1/3 pi's, then the rest should be, even though the drawing doesn't show it because it's not drawn to scale, this should be the remaining 1/3 pi. So clearly things are not symmetric because the distance here in terms of angles is 2 pi thirds. The distance here in terms of angles is 1 pi thirds. We are not symmetric. That means we're going to need 2 separate answers, 2 general solutions. We're going to have this general solution because they do form a straight line, and we're going to have this general solution because they do form a straight line. So our answers are theta equals, and you can start anywhere you want. We can go ahead and start here. That's pi thirds plus pi k. Remember, we only need to go half a circle to get to the next answer. And then to write this solution, you just need to start anywhere. Some people like to start in the positive angle. Other people, they don't mind negative angles. I think the textbook uses negative angles, so I'll go ahead and use that. So this angle right here should be, since it's going clockwise, is negative pi thirds. Right. And of course, you got to tell the reader what k is. So those are the trig solutions. Those are the solutions to that equation. So the skills involved to solving, I don't think will be the hard part. I think the thing that will take you a while to wrap your mind around is sort of writing down what the answer is, writing down the general solutions. It's going to be tough. It's going to be tricky. It's going to be confusing at first, but I promise you, if you just practice, you'll eventually get the hang of it. So go ahead and give it a shot, and good luck.